Hi everybody, welcome back to Multirate Signal Processing. So last time, this is where we stopped, basically introducing the DCT, and we saw that we get twice the subband density compared to the DFT because the DCT is only considering the positive frequencies in contrast to the DFT, which also covers the negative frequencies. So that means the distance between two neighboring subbands is only half as much as for the DFT, which can be seen also at the factor of pi over n for the DCT instead of 2 pi over n for the DFT. Okay, so next is the Z transform. So recall that the discrete time Fourier transform is defined as this formula here. So we have the infinite sum going over all samples in time and multiply each sample with e to the minus j n omega, where omega is our normalized frequency. And you also see this reduced notation where in the argument of the frequency domain signal capital X, you just have the normalized frequency omega instead of e to the j omega. Yeah, so here we can see that the expression e to the j omega is a complex number on the unit circle on the complex plane. Right? Magnitude e to the j omega is always 1, and omega is then the angle between the real axis and this complex number, the pointer to this complex number. Right? So in this sense, this omega then is interpreted as an angle. So it's a normalized frequency between 0 and 2 pi, if 2 pi is our sampling frequency. But conveniently, this can also be interpreted as an angle in the complex plane if we look at this number e to the j omega. Right? So very practical. So that also means we can replace this e to the j omega by a more general complex number z, which does not need to be on the unit circle, and this way we obtain the Z transform. So compare it. Here is the DTFT, and here just replacing e to the j omega by z, we obtain the Z transform. So here we would actually use the non-reduced notation. We replace e to the j omega with z here and also here. And this leads us to the Z transform. So that shows us that the Z transform is a more general transform, and the DTFT is just a special case of it. The special case for Z equals e to the j omega. So when you look at it, the Z transform simply turns a sequence into a polynomial, right? So when you look at this formula here, this is actually the definition of a polynomial. You have coefficients and you multiply them with a variable, and the exponent is the index of the sum. Except here we have the minus, so that means our variable would be z to the minus 1. So it simply takes a sequence and turns it into a polynomial. And this is relevant if you want to process it in Python. Right? In Python, for the Z transform of a finite length time sequence x of n can be represented by those program lines. So we can first import sympy for symbolic Python package. So this allows us symbolic computations like with a variable z. Then we import numpy as np. And then we just generate some random sequence, which is now our signal x. Right? So now the x consists of those 4 numbers. Doesn't really matter what numbers. And now we define the symbolic variable z using sympy. So you can see z is defined as sympy.symbols of the letter z. Right? So this tells sympy that it's a symbol and not a variable. Yeah, and then xz is now our polynomial made up out of our coefficients in x. So here you can see it, sympy.poly. So poly is a function in sympy, and it takes the coefficients in x. In this case, it flips it because we have this z to the minus 1. And then the variable that we take for the polynomial is z to the minus 1. Right? So it takes this as the polynomial variable, this sequence as the coefficients, and then turns it into a polynomial. And then we can see what's inside xz by just typing xz. And when you do it in a terminal, it displays the content. So here you can see the content, it's a polynomial. Here you can see the coefficients. So here you can see the last coefficients is first, coming from the flipping, times 1 over z to the third power. So this is also how we would expect it. The last coefficient gets the highest power. Then we get the next coefficient here, 0.56. This is this one here from our sequence, is multiplied by 1 over z to the second power. Here then the next to the first power, and then finally the first coefficient with a zeros power with a factor of 1. Right, so this is exactly how we would expect it. Here it prints again the variable used for the polynomial, and here's the domain. Not quite sure what RR means, maybe real. Yeah, so this shows us that we can actually use Python for obtaining obtaining polynomials. And let me just try it using Python. So let me first go into the suitable folder, cd multirate. Okay, so here we go. Then Python 3. So now we are in Python, and I can just import those first 3 lines and paste them here. Okay, so that worked. So here, of course, we have different random numbers, and then we turn them into a polynomial in this way. So I say copy, paste, and it doesn't complain. And indeed, this is now the polynomial that we get. So compare here, 0.02. This is connected with z to the zeros power, so that's appearing here in the end. And then the last is connected to the highest power, and that's indeed appearing here in the beginning, connected with 1 over z to the third power. So that works. So this is now also the z transform, right? We have the signal x consisting of those 4 samples, and xz is now our z transform. So now we are able to produce or compute the z transform in Python using SymPy. So that's very practical. So the z transform is more powerful because it is more general. Using it, we can also determine, for instance, if a system or a signal has a damping on it. In that case, the signal would be inside the unit circle, so if it decays over time. Also, we can compute the z transform even for unstable signals or systems, where we have a pole outside the unit circle and exponentially growing signals, which would not be possible for the DTFT because its sum would not converge. So if you have an increase of the signal, an exponential increase, then any infinite sum would diverge, and that's the case for the DTFT. But for the z transform, we just need to make sure that our z is inside the unit circle, and then we still have a converging sum. Yeah, so observe, this is the so-called two-sided Z transform because the time index n is running from minus infinity to infinity. Hence it already existed for an infinite time. Usually we can only deal with causal signals which start at a certain point in time, and this yields the one-sided Z transform which starts at n equals 0. So basically we set our starting point where the signal starts. So n equals 0 is also where the signal starts, and then it still might go on to infinity. Usually this infinity is just for convenience if you don't know how long this signal lasts, because any signal ends at some point, except if you have a theoretical signal. So if, for instance, if you have some exponential decay, e to the minus t, then it indeed goes on for infinity. So in this case, this is still practical, going to infinity. But for real signals, they all have a beginning and an end. Yeah, so the convolution in time becomes a multiplication in the Z domain. So again, very convenient, just like for the DTFT. If we take two sequences and convolve them, then in the Z domain, we get the multiplication of their two Z transforms. Right, so the Z transform turns the convolution into a multiplication, which is practical because the multiplication is usually a mathematically much more simpler operation. Yeah, so here's an example. We have a linear audio amplifier and an audio input signal. The frequency response of the amplifier can be h of z or h of omega, depending on the transform, right? So here we have basically the magnitude and phase of this amplifier at each frequency omega, or on the unit circle e to the j omega. Yeah, so this is usually what you have from the data sheet of your amplifier. And the frequency response or spectrum of our signal would be x of z or x of omega. So we input some music, for instance, and you can also compute the spectrum of the music using the Fourier transform, the DTFT, for instance. And then the output of the amplifier would be simply y of z equals x of z, the spectrum of the signal, times h of z, the frequency response of the amplifier. Right, so here you have it with omega, or in the Z domain, the same holds true, where you have z equals e to the j omega. So we basically multiply the frequency components of our signal with attenuation or gain at that frequency of the amplifier. Basically, h is the frequency response of our amplifier. So in this way, it's easy to imagine. So in this way, we use the Z transform basically like the DTFT, but as I mentioned, it's more generic, it's more general. Yeah, observe that unlike a convolution in the time domain, we can invert the multiplication in the frequency domain. This is a principle that is used, for instance, for equalizers who try to flatten the amplifier frequency response by having a frequency response which is inverse to the frequency response of the amplifier at each frequency bin. So here, if we have the frequency response, basically we can try to invert this frequency response to get the same amplification for each frequency. Yeah, we even have an inverse Z transform, which can be seen here. So this looks a little bit tricky because of this integral here. So this integral is a circular integral going over a closed contour C. So, and this closed contour C is such that all the poles are inside this contour. Right? Then we get the original time sequence. So you can see it's actually quite different from the forward transform because we have this integral. For the forward transform we had the sum, right? But the Z transform now is also a continuous function. So since we assume we have an infinitely long signal, the frequency domain is now continuous, right? So in the time domain, it's not periodic, and that means in the frequency domain, now we have a continuous function. And that's also why we need this integral here instead of a sum. Again, we have the z to the something, so here we have z to the n minus 1. So this minus 1 is different from the forward transform, and also the sign of the exponent, it's plus instead of minus. And then we have this factor 1 over 2 pi j, right? So 2 pi is the normalization, and j, yeah, basically 2. So it looks quite different from the forward transform. So yeah, this is what I just mentioned. C is the closed contour in the complex z-plane, which contains all poles of x of z in its inside, and its path is followed counterclockwise in the mathematically positive sense. So if you have a circle, then you would increase the angle to the positive direction, to larger angles. Yeah, so if we have a causal, stable z-transform x of z, then we know all poles are inside the unit circle, right? So that's a condition for stability. So that means our contour C can be simply the unit circle around the origin, because then all the poles are inside this contour. And then we can set z equals e to the j omega and let the angle run from 0 to 2 pi, right? So basically this function now makes our contour. So now we can apply an integration variable substitution. So instead of integrating over z and on this over this contour, we replace z by e to the j omega. And we have this function, and then we know that dz to d omega is j to the e j omega. So here exponential function derivative is basically the exponential function itself times the factor in front of the derivative variable. So that's why we have the j here. So that leads to dz equals d omega times j to the e j omega using the so-called Leibniz notation. So strictly speaking, we cannot really do this. It's more like a symbolic reformulation. We just bring d omega on the other side. But you can imagine, instead of infinitely small d's, we can have finitely small deltas, and then it's actually also possible in the normal math. Yeah, and that's since we have infinitely small d's here, this is called Leibniz notation. And this can be used then to substitute the integration variable. So here we have our original integral, or going over dz, and now we replace dz by d omega times j times e to the j omega here. So that can be seen here. So here I just did the substitution. So here is the dz replaced on the right hand side. Here I do this replacement, z becomes e to the j omega, and here too. So here instead of z we have e to the j omega, and then the same exponent here. Right. So, and then also the integration boundaries change accordingly. So now the circle goes from angle 0 to angle 2 pi. So now instead of going over this circle, this contour integral, we have a linear integral going from angle 0 to 2 pi. So this substitution now makes it much more easy to handle. So instead of a circular integral, we have now a linear integral, and we can simplify it now in the next step. So here you can see this j here in front of the integral cancels with the j at the end of the integral. So that's nice, because then we have something real valued. Then we have this e to the j omega, and this e to the j omega n minus 1. So the minus 1 here cancels with this e to the j omega. So what's left here is the e to the j omega n. Yeah, that's pretty much all. So then this is the result. And when you look at this result, this is exactly the inverse DTFT. Right? Surprise, surprise. We have exactly the inverse DTFT. And this means that for a causal stable signal for all systems, the inverse Z transform becomes identical to the inverse DTFT. So it's maybe not so surprising because we saw that the DTFT is just a special case of the Z transform. Yeah, so observe finite length sequences are always causal and stable, hence their inverse transform becomes the inverse DTFT, which is the coefficients of the Z transform polynomial. So the inverse Z transform for finite length sequences in Python can simply obtained by looking up the coefficients. So this is what I did here. So xz is our polynomial or Z transform of x, and dot coefs gives us the coefficients of this polynomial, and remember we flipped it, and here I flip it back, and then we should get the original. So let me try. So I just copy it and plug it into my terminal here with interactive Python, paste, and there we go. So here we can see this is our inverse Z transform, and here the first sample 0.02 is indeed the first sample that we had from our signal. Right, then here the second coefficient, and you can see they are exactly identical. So that shows that this really works as the inverse Z transform. So for finite sequences, this in Python gives us the inverse Z transform. Convenient, right? So now we can even do inverse Z transform in Python. So again, here we observe that we have transform pairings of periodic time gives us discrete frequency, where we have fundamental frequency and harmonics, and discrete time gives us periodic frequency, where we have a period of 2 pi. Right? In the case of the Z transform, we have a discrete time, and we get 2 pi periodicity in frequency domain, but continuous. Yeah, so observe in practice, we always have discrete finite signals, which are assumed to be periodically continued into infinity. Hence, our frequency domain will be discrete and periodic. Right? So this is what we get for the DFT. So this is an example. X of n is an exponentially decaying function starting at n equals 0 and with x0 equals to 1. Right, so this is actually an example of an infinitely long signal, so this is not periodic. So here it starts with the function is 0.5 to the nth power, right? And for negative n we have 0. So for n equals 0 we have 0.5 to the 0th power, then this becomes 1, right? x0 is 1, and then we have this exponential decay with this factor of 0. So this is easy enough. It's infinitely long, so it's only existing in theory, but we can still apply the Z transform to it, which I did here in the next line. So this is our x of n, right? And we also have the Z to the minus 1. So I also plug the Z to the minus 1 now inside those brackets because both have this exponent n. So this now becomes our Z transform. And when we look at the sum here, this is a so-called geometric sum, and it has a closed form solution if this summand converges. So if this goes to 0 for large n, then we have a converging sum. And this is the case as long as 0.5 times z to the minus 1 is smaller than 1. So if this is the case, then this is our solution. 1 divided by 1 minus 0.5 times z to the minus 1. Yeah, and this factor is smaller than 1 if magnitude z is larger than 0.5. Right? Remember here we have z to the minus 1. So if z is larger than 0.5, then this factor here becomes smaller than 1. Yeah, so if d is large enough such that this becomes small enough, then we have a converging sum, and this is called the region of convergence, or short ROC, right? Yeah, and this region of convergence also gives us important information about the signal. So here we can see that we obtain a pole of the expression for z equals 0.5. Right, so 0.5 is now the boundary case. For 0.5 it is just not converging, and indeed we get a pole here. So 0.5 divided by 0.5 is 1, so we have 1 minus 1, and then we have 1 divided by 0 goes to infinity. So in this way we can also see that see what time signal corresponds to a pole. Here an exponential time function. We have a correspondence, which is the exponential time function, gives us the pole in the z domain. Right, so this is what we just saw using this example. So here is just a short explanation about the geometric sum that we just saw. We had this form here, n went to infinity. This was our 0.5 times z to the minus 1. And we can see if we have such a shape, then we can multiply it by this factor a, and then this just means we have the exponent 1 up plus 1. And that's the same as if we would shift the index here by 1. And if we now take the difference between the shifted and the non-shifted version, we just get the first and the last index. So here we take as minus s, right? So here this is s, this is as. So what's left is just the last entry of as and the first entry of s. So we have a to the n plus 1 power minus 1. And then we can just reformulate it such that we bring this on the other side, and then we just have s, right, the sum. So s is a to the power of n plus 1 minus 1 divided by a minus 1. And that's our sum. Right, and here you can also see that if n goes to infinity, then all what's left is this minus 1, or if we changed order, then it's just 1 here. So this is the form that we just saw. This disappears if capital N is really large and a is smaller than 1, and all we are left with is 1 divided by 1 minus a. Right, so this is what we got. Capital N goes to infinity. When we have a stable system, then it disappears. Yeah, so here you have it, and you can see this factor here appears here in the Z transform as the pole location. So that's why we can immediately conclude from the pole location to this factor of this exponential decaying function. Yeah, so this is actually one easy way to do the inverse Z transform by inspection. You can just look at the poles, and you know that each pole corresponds to an exponential decaying function. Or if this pole is outside the unit circle, then it corresponds to an exponential increasing function. Okay, so this leads us to the short time Fourier transform, STFT. So the STFT is basically a DFT applied to short blocks of the signal. For that, the signal is first divided into overlapping blocks of length n with hop size m. Right. So here we look at short pieces of our signal. So here we can see the analysis function, and you can see this is basically the DFT kernel, e to the j minus j 2 pi over n k times n. So this looks basically like the DFT. But here we now have the signal with a time index m. Right. So here we can see here, this is the m. So we actually assume that our signal is longer, right? Here we assume it's not just ending within this block, but we assume that signal contains many of those blocks. And we basically address each of those blocks by this index lowercase m, right, which we can also see here, m times m. So m is basically a index at a lower sampling rate. So here we can also see that this is doing effectively a downsampling, and then with a step size capital M. And then the DFT is applied over a length of capital N. So here we see it doesn't have to be the same. We have a block size capital N and a hop size capital M. So this hop size can be, for instance, smaller, and then we get overlapping block. So we apply the DFT to a block of length n, one piece of our signal, then we shift it by m samples and apply it again. Right, so this is what we see here. So the x samples start at mn, and then they go on here with a sum index lowercase n. And then there's also this h of n, and this h of n is a window function of length n for improved filtering properties. So you can imagine this window function as fading in and out of this block. So in the beginning you would have small values or 0, and in the middle you will have larger values. So it looks maybe like the sine window or a raised cosine, just to give this yk better frequency resolution, meaning higher stop at attenuation. Right, so this is basically used as a sort of complex valued filter bank, which is oversampled in this case. Right, so it delivers us more frequency and time frequency domain samples than we had time samples. Right, so usually we also assume that the block size is an integer multiple of our hop size m, right, for convenience. Yeah, and for the synthesis, the overlapped blocks are added up using a so-called overlap add. So the synthesis equation is this. So we take our time frequency samples from the short time Fourier transform from the sequence of DFTs, apply the inverse DFT. Here you can see the inverse DFT going over the n subbands. Here we will get a block of n capital N time samples, and we again have to shift and add them. So here this is one block we are getting of time samples, n time samples, here with a normalization factor and another window, and then we need to overlap add all those blocks to obtain a reconstructed sequence. So again here we have the same shift, the hop size, and since the blocks are larger than the hop size, they overlap, and that's why we need to sum them up here. So here we can see this factor L. L is basically the number of times the hop size fits into our DFT block size. Yeah, and since we have twice this window, the window also has to have this so-called overlap add property, which means that if we apply it once and twice and shift it and add it up, it should add up to sum up at 1, so that we get the original sample values. So we can also see the STFT as a filter bank, but with non-critical sampling. Usually the hop size is really smaller than the block size of the DFT. Yeah, in the literature, the window function h of n is usually only applied to the analysis part, but here we also applied it to the synthesis part because this improves the resulting synthesis filters and is more similar to usual filter banks. Right. The corresponding Python function is scipy.signal.stft. So STFT is a function in the signal library, and it's very practical again that we have a function for it. So here's an IPython example. I will just continue using the Python 3 interactive shell here, Python 3. So that means I need to import numpy as np. And first we generate an artificial signal x. X equals, in this case, np dot arrange 32. So here you can see that arrange is a function in the library numpy, and it generates 32 numbers between 0 and 31. So here we can actually see it. This is our artificial signal, a ramp signal, just counting up. So then we can import scipy signal. So this is the library where the FFT resides. And then we can actually execute our STFT. So we could also first take a look at the help function of the STFT. So we do that by help scipy signal.stft, and then it tells us what it does. So here you have all the arguments, and here the explanations. So the first argument is the time series. The second argument, which is optional, is to give it a sampling frequency. So here we don't do it because we assume a sample signal anyway, and here the sampling frequency defaults to 1. Yeah. Then we can also say window function. So here the default is a Henning window or hen window. So there's also alternatives. Right, n per sec is an integer, and it's the length of each segment. So this is the length of the DFT, and by default it's 256. And n overlap is that's what we call the capital M. This is the hop size, and by default it's half the DFT length. So it means we have an overlap of 50%, an overlap of the DFT blocks. NFFT here is the length of the FFT used, and by default it's n per sec. Right. And it returns f, which is an array of sample frequencies. T is an array of segment times. So these are more interesting if we actually specify a sampling frequency. And then it returns zxx is the actual STFT of x. So this is what we call y here. Okay, so now we can just do it, apply it. So here we are using just a block size of 4, so it's rather short, basically fitting to our short signal. So copy and paste it here. So now we are done, and then we can take a look what's inside F. So here we can see, here we have the normalized frequencies from 0 to 0.5. 0.5 here in this case is the Nyquist frequency, because this normalizes the sampling frequency to 1. And T here is the corresponding numbers for our index lowercase m, right? So basically this is the time shift, the hop size. So first index of the first block is 0, then we go on 2 further, then we add number 2, and so on. So this is basically already the downsampled sequence. Yeah. So here the hop size is block size over 2. So this should actually be here in comments, because this is assumed by default. Yeah, we already looked at y. No, we didn't look at y. So let's do that. So we don't need the print because we are in interactive mode. So here we can see the result. So here we can see we have a matrix, and here we can see the output of the DFTs. Right, so here we have 1, 2, 3, 4, 5, 6, 7, 8, 16 samples. And we have 1, 2, 3 rows, 3 rows of each 16 samples. So that means we can now take the inverse. There's also the inverse DFT, or the inverse short time Fourier transform. So we just take the y. So now again we have the times, and these correspond now to the higher sampling rate. Here we can see all the samples are present, and xrec is now indeed our original ramp function. Right, so that worked nicely. So the overlap add worked, and also the overlap add together with the window function. So we have perfect reconstruction. So that works nicely. So going back to the output y, we can see that we have 16 samples. So that means that corresponds to our 16 time samples here. Here we can see we have steps of 2. So we get 16 time steps. So that means each row here corresponds to a downsampled time series. And that means each of those rows corresponds to a different subband, right? So this is subband frequency 0 to this one here, then subband 0.25, and this is for subband for normalized frequency 0.5, which corresponds to Nyquist. Yeah, so each row is a downsampled subband. Okay. So finally, I want to show you some translations of formulas to Python code. So we can translate formulas into Python code as in the following. So in the shell, we start Python by typing Python, as I just did, to get into the interactive mode. And then here's a simple example for a signal sequence X and a filter impulse response H. So here X is just those 4 numbers, H those 2 numbers, and then we can apply the Z transform. So we can turn the sequence into a polynomial or a Z transform using this formula, and here you can see the Python equivalent. So when we take this formula here, the Python equivalent would be, as we saw, using sympy, defining z as the symbol, and then turning our sequence into a polynomial like this. Right, so here we can see that we now have this polynomial. We can do the same using our impulse response h. Same thing, turn it into a polynomial. And we can also multiply it in the z domain. So here we have x of z times h of z. So remember, if z is e to the j omega, then we just do it element-wise in the frequency domain. In Python, we have two polynomials, and if we multiply two polynomials, we have to convolve their coefficient sequences. So this is basically what Python is doing for us when we say multiply. So we have xz. This is the polynomial for the x for x. So the z transform of x. Here the z transform of z, and here the star is the multiplication of those two polynomials. And here you can see the result. Right. So again, we get a polynomial. And then we can apply the inverse z transform to it. Remember, this was the formula for the inverse z transform. And we saw when we have a finite length sequence, as in this case, we can just basically read out the coefficients of the resulting z transform. So here yz is the resulting z transform. We take the coefficients and flip them accordingly. And this is what we get. Right. So these are just the coefficients that we just saw here in reversed order. So here 8, 10, 7, 4, 1. Here 8, 10, 7, 4, 1. And now we can compare it with the convolution in the time domain. Right, here the convolution in the time domain. We can also do that in Python using numpy.convolve x and h. And this is the result that we get after convolution. So when you compare it, it just fits. So 1, 4, 7, 10, 8 from the inverse z transform, and here 1, 4, 7, 10, 8 for the direct convolution. So the result is indeed identical. So that also shows that polynomial multiplication is the same as taking the coefficients of the polynomial and convolve them. So samples after convolution are identical to polynomial coefficients after the z transform above. Yeah, but in our case, convolve is usually faster than the symbolic calculation. So the symbolic calculation in the z transform domain is good for symbolic calculations, but if you really have numbers, then usually convolve is faster. Right. So here you have a convolution as sum, right? Here the star, here the convolve function is basically defined as the sum here, where the sum index goes down in the first argument and up in the second. And we can also write it explicitly as a sum, as I show here. So we have to first check for the length of the signals, and x is the length of x, and h is the length of h. And then we can compute the total length of the convolution result, which is simply the sum of the two lengths minus 1. So then we can initialize the result y with zeros of the corresponding length, and then we can make a for loop for our sum. So here this n is our outer sum index, and then here we have an inner sum L. So the outer sum goes over the result index range from 0 to degree minus 1 basically. Then this inner range, this inner index, goes over the arguments, and those arguments can have different length. So That's why basically I have to check here inside the sum what is the maximum length. So the inside of the sum is checking for that n, that L is in the right range, in the valid range of both arguments. So here the first argument we have n minus L, and that needs to be smaller than the length of x, and the second argument is simply L, and that needs to be smaller than the length of h. So then here we simply have the summation y equals y plus x of n minus 1 times h of L, or n minus L times h of L, and this is then the result. So here we can see also this those two for loops, this explicit sum calculation gives us the same result, 1, 4, 7, 10, 8. So again we get the same result as above as expected. So usually you wouldn't need to use this function because it's already defined as convolve in NumPy, but sometimes you have to explicitly program it. For instance, if you don't have a sequence of numbers but you have a sequence of, say, matrices, then you can program this convolution of two sequences of matrices in this way, right? So this works for all types of data, not just sequences of numbers, but also sequences of matrices, and we will actually use that later. So that's why this is useful. Okay, yeah, so maybe you can try out this for yourself. It gives you some useful tools for later. So it would be good for you to get familiar with those tools, know how to use them and understand them. And yeah, that should be it for today. So thank you for your attention, and see you next time.